Okay, so now we have an invited talk. Okay. Welcome everybody, ladies and gentlemen, to tonight's prize fight between computers and common sense. And we're very delighted to have Doug Lenat, who, as most of you know, was the director of the Psych project, which is the longest running project in the world to collect common sense knowledge. And it's also been a personal inspiration to me. I think that Psych is, even though Psych has endured much criticism, I think it's one of the greatest engineering achievements of AI. And I particularly personally admire Doug's persistence in believing in the approach and having the courage of his convictions, despite all the ups and downs of fashions and trends in AI. And I like to think that, and I think what we can learn, apropos of yesterday's discussion, what we can learn, I think, from the history of neural networks is that they also, as a community, had the persistence to have the courage of their convictions. And then finally, when there was enough compute power to realize some of their dreams, then that came to fruition. And I like to think that the cognitive AI movement is also maybe just a little bit behind the curve, and maybe some future wave will enable a vast jump in our capabilities. As Arnav Jala put it to me yesterday, our community is waiting for the second marshmallow. So you can think about that. So here's the prize fight. In this corner, we have Doug Lenat, the common sense champion of the world. And in the other corner, we have computers, or what Doug will tell us. And so I'm going to ring the bell and start the bout. Take it away, Doug.
Great, thank you. Can you all see the screen and hear me okay? I'm going to take that as a yes.
Yes, we hear you, Doug.
Okay, great. So what I wanted, and you can see my screen okay, right?
Yes, yes, we can see you.
Okay, perfect. So what I really want to talk about is the empirical scientific journey that I, and in many ways, our entire field has gone on in the last half century or so. And really, it's a series of hard lessons that were learned as a result of mistakes that were made. And so I want to take you through that journey. And I'll start with a story which was really significant to me and shaped my whole view of the field and why I work on this. When my daughter, Nicole, was born, when she was about 3.5 months old, she was diagnosed as having meningitis. And doctors at Stanford Hospital, I was a professor at Stanford at the time, doctors at Stanford Hospital really scared my wife and me in terms of essentially not really explaining anything, just telling us they had to do these various serious procedures and serious treatments and dangerous treatments and so on. And it was very frustrating. But coincidentally, fortuitously, Ted Shortliff, who was an assistant professor in computer science and jointly at the Stanford Hospital, had been working on the Mycin medical diagnosis expert system. And he had access to Nicole's chart. And so we put her data into Mycin. It came up with exactly the same diagnosis, exactly the same therapy recommendations and procedure recommendations. But the difference was, because it was a knowledge-based, rule-based system, we were able to look and see its reasoning chain step by step by step. We were able to look at alternatives and say, why didn't it come up with this diagnosis? Why didn't it recommend that treatment option instead of this more serious one, and so on? And that made all the difference in the world to my wife and myself. It was a real epiphany. And it seemed clear that AI, in order to be trusted and worthy of trust, would have to be able to do that same kind of reasoning, come up with its same kind of explanations, if we were really going to apply it to applications where life and property and other serious concerns were at stake. So at the end of the talk, if I forget, please remind me. I'll tell you the end of that story. But I really wanted to share that with you because it really was a very profound personal impact on what I do and why and what I have done. So the early mistakes that I made were largely in getting to the point of understanding why I needed to start on the Psych project. And those were in areas working with Cordell Green on automatic program synthesis from input-output pairs, the kind of work that Zohar Manna did, the kind of work that Alan Bundy has done pioneering work on and will be talking about later. And the problem was that if you actually know what program you're trying to synthesize, then it's too easy to hit the target. And even if you try and do the synthesis from natural language dialogue, which sounds vastly harder, if you have the target program in mind, then it's too easy to consciously or unconsciously cut corners and achieve the target you're trying to have your program right, but not really have something that would scale up. So as a result, oh, by the way, this wasn't unique to my experience. The expert systems people kept finding the same result. The robotics people did. That's why they basically had to give up things like going to shiny bricks and painting things shiny colors and only working on graph paper and filing bolts to a point so the robot could put the nut on the bolt once the bolt was filed to a point and things like that. So essentially, as a reaction to that, what I did was to come up with the idea of AM, automated mathematician, whose only goal was to discover interesting things, a kind of theorem proposer, not a theorem prover. And we gave it concepts from set theory, and it had heuristics for gathering data and deciding what new concepts were worthy of defining and exploring and so on. So for instance, it had a notion of list equality, which was recursive and essentially said two list structures are equal if their first elements are equal, and when you throw them away, what you have left is equal. And then if you come to the point where they both become empty at the same moment, then the original ones were equal to each other. So one of the things that it did was to look at random pairs of sets and random pairs of lists, which, as you might imagine, were almost never equal to each other. So it said, well, that's not interesting. So it wanted to generalize it so it would be equal more often with some weakened version of equality. So what it did was it basically threw away the test that the first elements were equal. So all it did was throw away the first elements repeatedly until at some moment, one list or the other or both of them would become empty at the same moment. If they became empty at the same moment, then the original ones had the same length. So it basically generalized equality into having the same length. And from there, it generalized set operations into arithmetic operations and so on. Or as another example, at one point, it had the concept of divisors of a number it had discovered and defined, the divisors of 12 being 1, 2, 3, 4, 6, 12. And one of the heuristics said, well, it might be interesting to look at the inverse image of functions in terms of the inverse image of extrema or near extrema. Well, what are extreme kinds of sets? Singletons, doubletons, tripletons, the empty set. Well, the inverse image of the empty set and singletons weren't too interesting. Didn't notice anything immediately obvious about the doubletons, but the tripletons were all perfect squares. So, the less you know about number theory, the more surprising that is. Didn't know anything about number theory, so it was very surprised. So it said, oh, well, let's not pass up a bargain. We can take the square roots very quickly. So it took their square roots, and again, much to its simulated surprise, those turned out to be the same as those numbers with two divisors, the inverse of doubletons under divisors of. So now that we had defined prime numbers, we found something interesting about them. It gave them a name and continued on. And in the course of running it, it came up with hundreds of little discoveries, mostly rediscoveries of things that were well known. Although one of my favorite experiences was at one point, one of my committee members, George Polya, said, oh, this thing it came up with involving highly composite numbers reminds me of something that a student of a friend of mine did. And he dug through an attic in his trunk in his attic, and he found some notes, a notebook that was actually from Hardy. And the student was Ramanujan, and Ramanujan had also come across the same regularity. So I took that as a sign that we were on the right track. But the problem was the heuristics themselves were stuck in and mired in and grounded in set theory. So as it began to discover more and more complicated things, those heuristics served it in less and less efficient good stead. So the next set of experiments I did involved mutating the heuristics, not just mutating the math concepts. And this was around the same era, 1976 or so, when I was an assistant professor at CMU, that I met this bright young graduate student, Pat Langley, who was also working on automated discovery. And that was a fun and fortuitous connection, and we've stayed in touch ever since. So Eurisco was also a lot of fun and discovered a lot of things, but the problem was that it kept petering out and slowing down, and pretty much due to its lack of common sense, due to its lack of world models, due to its lack of understanding of things in the world. Not so much factual knowledge even as models of the way the world works. So what is it that humans do to escape from brittleness? How is it that we escape from brittleness? Well, either we fall back on more and more general knowledge, like if, for example, my computer stopped working, I would, let's say, unplug it and plug it back in and hope that that fixed it or something like that. And we analogize to what might be superficially far-flung situations and experiences and knowledge that we have. But if you think about it, both of these escapes from brittleness are closed off to software because they don't have general knowledge to fall back on. They don't have far-flung knowledge to analogize to. And you heard some nice work from Ken Forbes and Joe Blass and so on about how that work has been continuing as well. But in some ways, I see work on analogy as being gated by having these large numbers of world models essentially to analogize to, not just specific facts to analogize to. So it seemed clear that we should prime the pump and essentially pull the mattress off the road so that traffic could proceed. And it was worth doing that if it didn't take too much effort to prime the knowledge pump and codify the, who knew how many, maybe millions of rules that we'd have to write in order to get the system to have those models of the world. So around this time, around 1983, I held a kind of mini Dartmouth conference at Stanford and invited all of my friends in AI, and they all came up with different estimates for how much effort and how much time it would take to do that priming of the knowledge pump. So I expected that these results would be very different from each other because some people, like for instance, Newell went into how many things could actually be burned into long-term memory in a human brain from age 0 to 7 or something like that. And some of the NL people did estimates based on the number of words that a speaker knows in their language and how many things they know about the words. I did some estimates with Alan Kay on the amount of content that's in a 1-volume desk encyclopedia and so on. Surprisingly, we all came up with numbers that were about the same, namely a few thousand person years of effort. So the bad news was that with a handful of graduate students, that basically would take me about 400 years to do. So that wasn't too good. But the good news was that if we knew enough or could find out enough about knowledge representation and automated reasoning and essentially use everything we knew at the time as a kind of null hypothesis, maybe we could actually accelerate that by a factor of 10, and then it would only take 4 decades instead of 4 centuries to do. So that's pretty much what we did. I had the opportunity to become the principal scientist at MCC, the Microelectronics and Computer Technology Corporation, because right at that time in the early 1980s, Japan had threatened to do in computing, hardware, software, and especially AI, what it had just finished doing in consumer electronics and the automotive industry, namely wresting control away from the West. And so Congress immediately acted. That's how you could tell it was a long time ago. Congress immediately acted, did something, namely they passed the NCRA, the National Cooperative Research Act, which said, hey, all you large American tech companies, normally we would prosecute you for antitrust violations if you dared to collude on R&D and technology development, but we promise you for the next 10 years, we won't do that. So MCC sprang up a research consortium with about 20 large American companies as its member. And I was able to get that larger team working for a decade without having any kind of pressures for raising money or publishing papers on any kind of schedule. So that was wonderful. And then at the end of 1994, the fifth generation effort essentially wound down in failure. At the end, if anyone is curious and wants to know, I can go through the factors that led to that. But we spun Psych out of MCC. And for the last few decades, we've been doing it at Cycorp as a private company with about the same effort, maybe a little bit more effort than we even had at MCC. So this is one group where I don't need to go through in any detail the power of using symbolic knowledge representation and symbolic reasoning and so on. But just to summarize in a few bullet points, you get the power that I was mentioning from my story about Nicole, namely the step-by-step reasoning of conclusions that are made. If you have a derivation, even if it's long, you can still trust it. And you don't have to have just the top answer magically appear at the top of the magic 8-ball. You can have the top N answers, and you can have pro and con arguments displayed for each answer. And you don't need big data to train on. In fact, if you're doing counterfactual reasoning or what if reasoning and so on, there might be no data that you can train on. And still you can make reasonable inferences. So let me give you a couple quick demos. I'll give you the first demo of this right now, just so we're on the same page as far as what I'm talking about when I talk about this sort of step-by-step reasoning. So if I ask Psych something like, can an upside down coffee cup hold hot coffee? It'll say no, basically, because the coffee is denser than the air and it's not being supported and so on. And if I change that to something like helium gas and ask it, then it'll say yes, essentially for the converse reason. And underneath all these generated NL sentences is the actual knowledge that's contained in a logical representation. You can think of it as predicate calculus, if you want, that basically contains all the same knowledge. And so Psych is doing all its reasoning in logic, and then it's just generating these natural language sentences. In fact, most of the time that you see is being taken up by the NL generation. Or if I ask, would a human dislike touching an incandescent light bulb when it's on? It's like, yes, because humans in particular don't like feeling pain, and that touching event would cause pain because the light bulb is too hot when it's turned on, and so on. So that's the short demonstration of what I mean by being able to give its actual explanations of the reasoning it's doing, of the answers it's coming up with. And I could give you, and I will give you in a minute or two, some examples of pro and con reasoning, not just finding a single answer. On the other side, the statistical machine learning people who do training of deep neural nets and so on have going for them that often that suffices for many problems. That's actually adequate. And if it is adequate, it's generally much, much more cost effective to apply that paradigm, that technology, rather than symbolic reasoning and symbolic representation. So if you think not just about the strengths, but about the weaknesses, those sorts of statistical machine learning systems are very brittle in many ways. Anytime you use Siri or Google Assistant or anything like that, you see that kind of brittleness, or there are all sorts of humorous examples. You can see from GPT-3 and so on, and maybe less amusing ones from Microsoft Tay that very quickly trained on big data and became genocidal and racist and so on, and had to be taken down a couple days after it was turned on, and so on. But anyway, another example of that, anytime you use Google, you can see these kinds of, for instance, I didn't really go through the last couple prime ministers, but if you ask who was the prime minister of the UK when Boris Johnson was born, if you ask Google, you'll get something like 34 million hits, none of which actually give you the right answer, almost all of which tell you when he was born, June 19th, 1964. And then if you as a human type into Google a new question of who was the prime minister of the UK on that date, then again, you get tens of millions of hits, by the way, most of which still give you the wrong answer because Harold Wilson is so much more famous than Alec Douglas Home, which happens to be the right answer. So that kind of machine learning suffers if there is no data to train on, if the events are very rare, like let's say the release of nuclear weapons, which fortunately there's not much training data on, or if you're trying to fix a car or a human body that has 2 faults or 2 diseases or 3 diseases happening simultaneously that obscure each other and so on. Or if you're asking hypothetical counterfactual questions where there is no data because the things haven't happened yet and so on, or you're trying to generate plausible scenarios, either going forward in time or working backward from some event, either that you want to have achieved or that you want to make sure doesn't work, doesn't happen, and so on. In this case, looking for abductively plausible ways that that bad event might happen that bottom out in today's world in events which we could actually watch out for and put controls in place to watch out for. So I already mentioned some of these, but think of these as opportunities, not just as deficits, as problems or limitations or weaknesses with statistical machine learning, but think of these as opportunities where it could beneficially partner with the kind of AI that most of us are working on, because those other kinds of AIs only have the veneer of intelligence, not real intelligence. But to be fair, the same could often be said for the kind of cognitive AIs that we work on, the kind of left brain, to take a kind of metaphor. I understand that neuroscientists might squint a little bit at these sort of characterizations, but think of them as metaphors of left and right brain reasoning, caricatures rather than actual claims of very clear separation of functionality of the 2 hemispheres. So what are the weaknesses of this sort of symbolic AI? Well, one of my favorite examples was the Alain Bonnet skin disease diagnosis system. And at one point we told it about this patient and it asked these questions, and we said, to the first one, yes, and then reddish brown, and then more on the trunk, no. And so eventually it diagnosed the patient as having measles. And the reason this was funny was that this was the patient, my rusted out old white station wagon that I had bought from Ed Feigenbaum a few years before. And the point is that even our types of AI can make mistakes that humans wouldn't make if they don't have the right general knowledge, if they don't have the right models, if they don't have a deep enough understanding of context. So if you wanted to list the different ways that symbolic AI can sort of break down, one is if you build stovepiped knowledge-based systems where you use idiosyncratic terms, and so the rules or assertions in one that should be triggering in another don't actually trigger because they're using different vocabulary. Or even worse, the converse of that, where they do use the same vocabulary, but they mean slightly different things by the different terms and so on. So then you have the equivalent of ships crashing in the night. Also, if the cost of building and standing up the application is important, the machine learning system might be 1/100th the cost of and the time of the knowledge-based approach. And the speed with which the knowledge-based systems run have historically been much slower than the speed with which the statistical neural net systems run. Also, these systems don't do well if you are talking about nested modals like believes and knows and wants and desires and dreads and so on. If you're going to do real-time knowledge revision and elaboration, tolerance is a requirement where new knowledge might come in that modifies things even as you're working on a problem, and so on. So all of these really have been addressed in the last several decades, but the kind of thing I'm talking about are not really new. They're things that AI scientists knew 40, 50 years ago. If you look at Rosenblatt and at Minsky and Pappert's work on perceptrons and multi-layer neural nets and so on from the 1960s and even the late 50s, you'll see almost the same kind of architecture and the same kind of results we see today. So what were they waiting on? Well, they were waiting on computers to get fast enough, for GPUs to come into existence, for storage to be cheaper, for big data to be available, and so on. And similarly, the philosophers from the 1800s were pretty much waiting for computers. But in the 1900s, the 1960s, the expert system folks came up with very much the same architecture that we use today. So what were they waiting on? Well, they were also waiting on computers to get faster, but they were also waiting on pragmatic solutions to problems like inconsistency and modal reasoning and so on. And they were waiting for someone to drag that mattress off the road and prime that knowledge pump so that they could start from that base of real world models and real world knowledge rather than starting as a tabula rasa every time they wanted to build a new system. So this is pretty much what led to the Psych project back in the early 1980s. I won't go through the numbers in a great deal of detail, but we have spent about 40 years. We spent about $250 million. We've been working as a tight team rather than a set of loosely affiliated independent researchers and so on. And we've gotten pretty far. I gave you a couple of examples. I'll give you a couple more demos as we go along, but just to understand the basic idea of what I mean by symbolic reasoning, which I think all of you in this audience really do understand. Suppose we're looking for videos of a smiling man and we have captioned videos. We don't actually look at the videos, we just look at the captions. And one of the captions is, Chris watched as his daughter took her first step. So you believe probably on there somewhere is a smiling man. Well, why do you believe that? Well, it's because you have a few pieces of general knowledge, like parents love their children, taking your first step is an accomplishment. And when somebody you love has an accomplishment, it makes you happy. And when you're happy, you smile. And so if you have some sort of representation of those pieces of knowledge, and you have some engine for grinding through the deductive consequences and the closure of those assertions, then you'd be able to find that match. Doing it would become trivial. But if you don't have that knowledge, finding that match is more or less impossible. It's not like Google could find this kind of match if it just added another 50,000 servers or something like that. So why do I believe that we're nearing the end of priming the pump in this way? If you look at applications that we're working on, most of the time we're putting in application-specific knowledge nowadays, very rarely general knowledge. And if you look at a particular application like this one for the Cleveland Clinic, the amount that we had to add was down at the less than 1% level. And conversely, if you look at the system answering a typical question, 95% of the knowledge it's drawing on was knowledge that we entered decades ago, long before we started that application. And the reason we use an expressive representation language rather than something which is more efficient, well, if you think about it, there are all these different logical representations and other representations. So obviously one very, very general representation is natural language. We all have read or watched plays like Romeo and Juliet in natural language, and then we could answer lots of questions about it. So, if I asked you questions about, does Romeo believe that Juliet is dead at a certain point or something, you'd be able to answer that correctly and tell me why. And and so on. So natural language is a perfectly good representation if you have enough knowledge of the world to be able to process natural language. That's a kind of catch-22, where if you don't really understand much about the world, then you can't get as much out of the natural language. So there are various kinds of questions you could ask and answer just using text processing, just using things like latent semantic analysis and so on. But if you really wanted to answer some of the harder questions, you'd have to use some of these more symbolic, more logical representations. I still call them limited logics because most of these are less than first order logic, and really first order logic isn't really adequate either. But what separates all those limited logics is answers to questions like, can you have variables? Can you have both universal and existential variables? Can you nest them arbitrarily? Can you have function symbols whose values can be treated as though they were full-fledged terms? Can you have relations of varying arity, not just binary relations? What are the different ways you deal with negation? How do you handle exceptions and contexts and elaboration tolerance and truth maintenance? And so why is there all this explosion? Why is there a plethora of these limited logics in use? Well, it's pretty much a question of efficiency. If you think about it, every representation represents a kind of trade-off in this curve between how expressive is it? How much can you express how easily in that representation versus how efficiently can computers reason with things in that representation? At one extreme, you have natural languages. At the other extreme, you have computer languages. And what we really want is something which is expressive and efficient, but there is nothing which is expressive and efficient. And in fact, as I mentioned, even first order logic isn't really expressive enough. Almost any news article about the Ukraine or almost any news article about politics today, you'll see the importance of being able to represent what X believed, that Y believed, that Z wanted this person to believe, and Y. And so basically, first order logic just isn't adequate. But the good news is that we've found ways to speed up reasoning with representations in higher order logics. So we can functionally have the equivalent of both expressivity and efficiency. The zeroth order answer of how we do that is to have multiple representations and represent everything in multiple ways and do that redundantly. And then we have different inference engines, different inference procedures, some of which operate on this nice, clean epistemological level language, some of which operate on this grubby, efficient, heuristic level language. And we have ways of mapping back and forth between the different representations. So that slows us down. But on the other hand, when we're actually doing reasoning, once we've got all these redundantly represented, it speeds up reasoning and makes the reasoning possible very quickly. So you can think of that as like one idea for how we're able to recoup some of the lost efficiency. By now, we have over 1,000 of these reasoners. Some of them are very general, like caching, the Kleene star, the transitive closure of transitive relations, so that we can answer those kinds of questions in one step instead of n steps. Some of them are fairly specific, like how to balance aqueous chemistry equations. Don't come up very often, but if you have that, then it's very, very efficient when one of those does come up, and so on. Another way we improve the speed is not by extirpating, not by removing knowledge from Psych's brain, but rather by adding meta and meta-meta knowledge, strategic and tactical knowledge to help guide the reasoning process. And also, we contextualize things so that not everything is dumped into an enormous sea of assertions and rules. The knowledge base is more like a quilt or like tectonic plates on the Earth, where it's divided up into locally consistent contexts, and then there can be interstices between them and slight inconsistencies from one to its neighbor, and so on. We've done a lot of other work. I won't go through too much, but I said I would do a couple more demos, so let me go through another demo or at least a couple examples where I show you that we are able to deal with conceptual works like Romeo and Juliet. We are able to deal with modals and pro and con reasoning. So for instance, if we ask, what are the apothecaries motives for and against selling lethal poison to Romeo? Well, the incentive is that the apothecary's family is starving and you don't want your loved ones to starve. And the disincentive is at the time, Romeo was living in Mantua, the apothecary was based in Mantua. The penalty for selling lethal poison in Mantua was death if you were caught. And in general, people don't want to die. So again, if you look at the cycle that's involved here, you can sort of see where it's sort of representing things like at the time of this particular fictional context, the penalty in Mantua for being the seller of lethal poison was basically being executed. And one of the things at the very top was people don't like being executed. So it's not really super deep reasoning, but this is a good example of what I meant by pro and con reasoning. And then if we look at counterfactual reasoning, like how would Lord Montague have felt about the wedding of Romeo and Juliet if he had known about it contemporaneously? Well, he would have felt high abhorrence. And a lot of that is due to the fact that the parties were enemies of each other. And so if, for instance, we want to reject one of those premises, we could basically just sort of look and see where it was. Oh, here it is, where they were mutual enemies. So we say, well, suppose the two houses were not mutual enemies. Now, if I re-ask that query, he would have felt vague positive approval toward it because it would be bringing together two important noble houses in the city and so on. So here you can see Psych is doing the reasoning. It's doing it relatively fast. It's doing it relatively correctly. And it's able to explain its reasoning step by step by step. If I give one other quick example of what I meant by natural language requiring common sense, if you look at a sentence like, Tom was mad at Joe because he stole his lunch. Well, who stole his lunch? Presumably, Tom was mad at Joe because Joe stole Tom's lunch. And if I change the because here to so, and I ask the question, Tom was mad at Joe, so he stole his lunch. What are the reference of the pronouns? It's, well, Tom was mad at Joe, so Tom stole Joe's lunch to get back at him. So very simple models of revenge and anger and crime and people owning resources and so on are really all you need to be able to answer these sorts of questions. So the real story I wanted to impart in the last part of the talk is some of the mistakes we made, just rapid fire listing of some of the lessons we learned along the way going down this path. And one of the first things we did was try to represent the content of encyclopedia articles. And then we realized that no, actually what common sense and general knowledge are like the complement of that. It's everything other than that. So you can look at the Encyclopedia Britannica article about water, and it's like 11 pages long, and it never says anything about things being wet. And once they're wet, they stay wet for a while and dry out in the sun and things you know about water. So really, it's representing not the black space of the actual printed text, but rather the things that the authors didn't say, the things that are essentially in the white space on the page was really the important thing. And often we would look at encyclopedia articles or newspaper articles or advertisements and try to ferret out the pieces of general knowledge that they assumed the readers already knew. So anytime you see pronouns like I showed you, that's a good sign that there's some piece of common sense that the writer expected you to be able to apply to do that disambiguation of what their anaphoric reference were. Or if you see a couple sentences in an article like Fred robbed the First National Bank, he went to prison for 10 years, the writer expects you to infer that Fred was caught, he had a trial, he was found guilty, he was sentenced to prison, and so on. And if the next sentence says something about the judge, now you know about who the judge is because we know that there was a trial and presumably the trial had a judge and so on. We also sometimes look at things like National Enquirer and Weekly World News articles and say, what do they assume you don't know about the world, to be able to believe things like a World War II bomber was found on the moon and things like that. Some of our other mistakes early on were agonizing over our upper ontology, that, out of the millions of terms, agonizing over the top 100 or so terms and so on. And of course, it's not just us who has made that mistake and fallen into that trap. A lot of the people who've built ontologies have focused a lot of their effort on just the upper part of the ontology. Partly, I think, because Aristotle made a big deal. But Aristotle was right about a lot, but he was wrong about a lot. And he was, I think, wrong about his beliefs about the importance of upper ontology. So I would sort of throw that away. I think a good example of that was at the Japanese 5th generation project, they had this ontology that was trying to fast follow what we were doing with psych. And at the very, very, very top of their ontology, the first distinction was between things with souls and things without souls. And it turned out that big trees had souls and small trees didn't. So that was their top level split. And despite that very different way of organizing knowledge, by the time you got down 12 levels in their hierarchy and our hierarchy, it was pretty much the same kind of knowledge that was being stated. And that's why we can get along with people who have different ways of carving up the world mentally, cognitively. Another example of how choices you make in your upper ontology really just affect the efficiency of your system. You can have a horrible term like the government of France in the year 2009. It would be better to split that apart and factor out the during function and the government function and so on. But you could get by with this plethora of terms if you wanted to. If you look at, say, the ICD-10 set of the ontology of medical terms, medical procedures and conditions and so on, you'll see a lot of these horrible terms because they don't factor it the way that I'm saying here. Extreme case for philosophers who define these sort of Gedanken experiment concepts like grew and glean. You can still represent the fact that grass is green, even if you don't have the concept of green. You just, in this case, would have to say that grass is grew by day and glean by night, and so on. So you really want to be as unambiguous as possible, because otherwise your deductive closure is either going to be wrong or small or something like that. And so when we developed our representation of our ontologizing of physical containment, originally we had one in relation, but now we have something like 75 specializations of in, or something like with. We have dozens of different species of with relationships or has relationships, and so on. So we also don't want our ontology to be too large. It's bad enough that we have several ways of saying something is yellow. Every time you have multiple ways of saying something, you have to take the trouble to write the interstitial axioms that relate all those to each other. So how do you draw the line of what deserves to be in the ontology and what doesn't? Well, following, say, Pat Winston's arch learning program with looking at boundary examples, one of the things that we look for are boundary concepts of things that either just barely deserve or just barely don't deserve to be in the ontology. Like black cats deserve to be there because there are lots of things involving superstition and witches to say about them. White cats, well, maybe all you really want to say is they're white and they're cats. So maybe that's a place where in one case you put an explicit term and in the other case just represented compositionally if someone wanted to talk about white cats. As I said, we had to move on from frames and slots from knowledge graphs as the representation we were using in the early 80s and actually in the 1970s, even with frames and slots and so on, and had to move to this more and more expressive language. You can think of it as analogous to going from machine language to higher and higher level programming languages. And one advantage is that you can have little NL templates for these higher arity predicates. So if you have a template like this, you can generate a sentence like that, which is a nice natural sounding sentence compared to just representing as a set of triples that don't really stand on their own. We had to move away from negation as failure. We had to embrace different types of quantifiers like there exists exactly or there exist at least. We had to distinguish element of from subset of. We had to be able to reflect the reasoning process that was going on and represent nested modals, like I showed you. In general, kicking and screaming, we were led to this higher order logic and finding ways of making it faster. Similarly, our interfaces got more and more complicated, from simple node and link graph interfaces to much uglier sort of frame and slot type interfaces over the years. And as I said, one of the key insights was not to play the game of where on this trade-off curve should we be, but rather having multiple representations, some that are used by the ontological engineers who may not even know programming, some who are used by the inference programmers, almost more like the Morlocks from the time machine. And I'm sure you're all familiar with different representations. Sal Amaral and others talked about different changes of representation and how they can make problems easier to solve if you pick a good representation, and so on. So I will mention a few other sort of painful lessons we learned. One was there were all these inference parameters, like maximum amount of time before you quit. Are you allowed to introduce new terms in the course of answering this question, blah, blah, blah. Eventually, there were over 100, like 150 parameters. Every time you asked a psychic question, that was crazy. So we did an experiment, and amazingly, there were 6 combinations of those 150 parameters, which essentially sufficed for the last million things psych had been asked, that either got the same answer or psych originally didn't get the right answer and neither did this. And so basically, that meant we could essentially replace 10 to the 48 different possible settings with one single 6-position wheel. So that was sort of amazing. Another thing was that anytime the general theorem prover was being asked, that meant that all those HL module reasoners had failed, and it took too long, and it never succeeded. So quietly, about a decade ago, we turned off the general theorem prover, and no one's ever really missed it since. So that's another sort of lesson that was hard to learn lesson. Another example was believing that if we shared just the taxonomy of terms, then people would understand why they needed the rest of psych. But in fact, that didn't really work out too well. And a lot of groups, I think Ken Forbes's group and a lot of robotics groups and so on are still using OpenPsych, even though we released it as a bad example of like why that's not really all you need. But that's okay if they're getting value out of it. So obviously we had to deal with context. As I mentioned, things are often only true in one context and false in another. If it's getting on Christmas time, and if your spouse says, oh, can you pick up some of those red flowers I like? And you come back and you say, hey, guess what? I found out that poinsettia flowers are in fact green. It's the leaves that are red. That's not going to win you points with your spouse. Okay, so having ontologies in which apes are monkeys and vice ontologies where monkeys are apes is really valuable. Having ontologies where people and monkeys aren't related is actually valuable. Having ontologies where poinsettias are red flowers is useful. So you need to divide up your knowledge base into these regions or territories or quilt segments or tectonic plate segments where each of those might be consistent, but there can be inconsistencies across them. So we have to move from global consistency to this notion of local consistency, much like, the surface of the Earth is globally spherical, but you still live your life as though it were flat because it is locally flat. So let me just skip over a couple of these things, obviously dealing with argumentation and so on. And one of the things that we also learned was everything I just said, sometimes take with a grain of salt, because sometimes you can choose a limited representation and it works. Sometimes you can choose a more rigid system, a less expressive system, and it suffices. So the last thing I wanted to talk about, though, was the kind of synergy between the two types of AI that I was talking about, where you might have some ML system that is coming up with hypotheses about correlations between a patient's symptoms and the disease that they suffer from, but doesn't understand why, because it's just statistical. But then psych can use its knowledge of reactions that occur in the body and what polymerizes what, and what catalyzes what, and so on, to come up with step-by-step arguments for why this particular mutation of this part of the DNA might have led to this kind of condition like osteoporosis early in life. And along the way, it may have made some predictions that you can now go back to the data and test for. So that's very exciting. And I see that kind of synergy as the sort of path to AGI going forward, to a general intelligence going forward. So let me stop at this point. I'll just give you a hint of, I suppose, since we're talking about a kind of somewhat academic audience, I should probably talk about the mistakes I plan to make going forward. And I'll just mention a couple things. One is focusing on Psy Power Tools to help people lower the bar for building and editing psych applications. One example is a kind of abductive reasoner. If psych comes up with the wrong answer to a question, even someone who doesn't understand logic or know much about psych can basically say, oh, here's the answer you should have come up with. And then psych can abductively say, oh, well, I would have come up with that answer if any of the following 10 things had been true. And then that let's say, human expert can say, oh, yes, number 7 is true. So now, without understanding anything about logic, someone was able to debug and improve and educate the system. So that's really what I wanted to focus on. I hope that you got some of the useful takeaways around this. And I will just close by mentioning the story with my daughter, Nicole, had a happy ending. She lived through the meningitis. And in fact, in a few days, we're going out to San Diego to have Thanksgiving dinner with her and my grandkids. So let me stop at this point, and I'll be happy to take questions if we have time and if there's some questions. Thank you.
Okay, Doug, thank you for a knockout talk. And I hereby award you the virtual belt for winning the fight. Okay, so question, Dustin.
Hi, Doug. Whenever I think this is the second talk I've seen of you, Psych is so impressive. So I know Cycorp is focused on enterprise solutions and open psych, and I've also tried to use like NextKB. Do you have any plans to maybe make things more available in some capacity to like researchers who might want to use this? So other tools like OpenAI and GPT have like paid APIs. So I think there's like a lot of solutions. But just from the website and other stuff, if we don't want to use NextKB, is it kind of just accessible via enterprise companies? Just if you could speak to that in any capacity, that'd be fantastic. Thank you.
So it definitely is a good question, by which I mean a very difficult to answer question, because on the one hand, I absolutely want this to be as widely used as possible. As you may remember from Dr. Strangelove, if you don't tell people that you have a doomsday device, the whole point of having a doomsday device is lost, and so on. So the whole point of psych will be lost if it isn't widely used and hopefully at some point universally available to everyone. So we have to balance staying in business by focusing on enterprise applications and so on, with hospital chains, with robotics companies, and so on. Balance that with the desire to make as much of this as possible available to researchers, available to everyone who wants to use it. So we're thinking about how we can stand up a site where people can play around with Psych, go through some of the training modules, and so on the one hand. And we're looking at things like a paid API model or some very low cost research license that would let people get access to it. So this is something which is really top of mind for me. And it's one reason, why I sort of come out of my burrow to give this talk, because I really want us to start keeping a higher profile, communicating more with the research community in general, and trying to find ways that we can collaborate with researchers.
Thank you.
Okay, Michael?
It's Mike Cox. So in 1983, you, along with Randy Davis, John Doyle, Michael Gunezareth, Goldstein, and Howie Schroeb, wrote a textbook on expert systems, building expert systems. You had a rather remarkable statement in there at the end of one of the chapters, and it said, once self-description is a reality, the next logical step is self-modification. Small self-modifying automatic programming systems have existed for a decade. Some large programs that modify themselves in small ways also exist. And the first large, fully self-describing and self-modifying programs are being built just now. The capability of machines have finally exceeded human cognitive capabilities in this dimension, and it's now worth supplying and using meta-knowledge in large systems. Now, we can ignore the prediction about exceeding human cognitive capabilities, but you mentioned only on slide 62, I think, about meta-knowledge, and it seemed to be talking about efficiency heuristics. What other ways is meta-knowledge or meta-rules used in psych and in applications? If you remove them, would it be that much different?
Yeah, so I certainly appreciate being reminded of that. I hadn't thought about that in a long time. I'm definitely going to blame any hyperbole on Randy Davis and Howie Schroeb on the others, and Mike Gunezareth. Just kidding. But I think actually the main point of that really still stands, which is the kind of systems that we're talking about have the ability to introspect on their own reasoning in ways that we as humans don't, or at least we only rationalize that we do, and so on. So in that sense, I believe that the symbolic representation and reasoning systems we have and that we've had for many decades actually are in some ways superior to what humans are able to do in terms of cognition. Obviously not in terms of performance, in terms of being able to drive cars and operate on human patients and so on, but in terms of that ability to fully introspect on their own reasoning and understand their own reasoning. So I believe that is important. That is a capability that these systems need to have and can have. And what I was trying to get at was that there are various kinds of meta-level knowledge. And if you want, you can think of contexts of microtheories as meta-level knowledge, which is, oh yes, this piece of knowledge, this rule is useful in, let's say, a sports competition situation, but not a scientific lecture. So if you liked something I said and half the audience stood up and screamed, that would be very strange. Whereas if you were at a soccer match and something like a goal happened and the audience didn't stand up and scream, that would be very strange, and so on. So you have knowledge which is true in one context and false in another, true at one time and false in another, true at one level of abstraction and false at another. If you're in the car behind me, I want you to have a Newtonian or even Aristotelian view of physics, even if you're a physicist. Okay, I don't want you to think of my car as an eigenfunction. I want you to think of it as an impenetrable object, and so on. So that's another important use of meta-knowledge. Another one is being able to reflect on the processing of what has been tried already and trying to come up with this problem. What is the system doing? And so basically, there's all sorts of meta-level reasoning which can come into play, which I see as a key, because if you want to speed up the reasoning of a system, instead of thinking of how can I pare down what it knows so it won't be cluttered up with all this irrelevant knowledge, just think in terms of what additional meta-knowledge could you apply. So if I say, is Joe Biden standing or sitting right this second, maybe after a few seconds or whatever, you'll decide, oh, I don't know. But in fact, it never crossed your mind to worry about how many legs a spider has or anything like that, because you have a good enough set of meta-knowledge to very quickly decide when the point of diminishing returns is on continuing to cogitate on answers to questions like that.
Okay, related to that, we have a question from the Slack from Anil Murthy. And Anil asks, do you think there's a possibility to design an objective metric for what constitutes a good context?
So I would say that the key there is almost a foreground background switch, where think in terms of the dimensions of contexts, some of them already, like time and space and type of event you're at, and level of abstraction you're reasoning at, and level of security you need. So, so basically for each of those different dimensions, you basically can ask the kind of question you're asking and start to answer it dimension by dimension. And the real problem, the real core question is, if you know, let's say P is true in context C1 and P implies Q is true in context C2, how do you decide in what contexts it's reasonable to believe Q is going to hold true? And so if you answer that question dimension-wise, as sort of the work of Cindy Loisel and Paul Cohen and Mike Hunes and others have been working on, I think that's really the key to cracking that problem.
Okay, thank you. And that's all we have time for, but the discussion will continue on the chat. Doug, if you want to stick around and take a look at the chat, that would be great. And let's thank Doug for a fantastic talk.
Thank you.